So thank you very much for letting me speak here. It's a pleasure. Last time I was here, I gave a job talk about more biology. So now I'll do some about deep learning in connection to the previous talks. And my title of my talk, it was pretty long, but I just used arrows to short it. So how over-parametrization of the network makes bad local minima in some way. What's bad, I will define later, vanish. OK, so let's get started. So in deep learning, it was also mentioned before, many cases you can get state-of-the-art performance on deep neural networks and data sets such as ImageNet, CFAR, with much more parameters than data samples. Okay, for example, the original AlexNet that had the seminal results in 2012 had 60 million parameters, and it was used to fit 1.2 million samples. Okay, even if you just count only the last two layers, it's still, I think, 16 million parameters or something like that. So it's still quite a lot of parameters to do this fitting task. Also, it's more recent, slightly recent work, ResNet, also 20 million parameters, 50K samples on ResNet, like about sometimes the order of 1,000 times more parameters than
this is 60 million independent parameters.
In the what?
It's 60 million independent parameters.
Yes. Yes.
Not weight.
Yeah, not weight. Not the cons. Yes. OK, so that's in deep learning. And also, this is my only part I'll mention biology. It's very speculative. Maybe it's related. I'm not sure. So we know in the biophysical level that there's a lot of degeneracy, like in parameters, and different models. Sorry, the same model with different sets of parameters can create the same behavior. And it was observed in small networks, and also my work a bit with neurons and ion channels, that you get a lot of degeneracy in those models. So some over-parametrization there might be suspected, that you have much more parameters than you need to generate a certain function. That's like in a speculative low level. Also, that's very now completely speculative. This is Hinton back of the envelope calculation. I just put it here because maybe it's in a very high level. If you have 10 to the 15 synapses and you count the number of milliseconds in 100 years or something, which is kind of 1 millisecond is, if you think the brain is a giant recurrent neural network, and with 1 millisecond time being, then you have much more parameters, your synapses, than the number of samples. OK, so it's like completely back of the envelope calculation. Some small motivation maybe why is it. What? Sorry?
Compared to evolution.
To evolution, yeah. OK, I find it funny, so I just put it here as a joke. OK, so in deep learning, I'll go back to deep learning. So there's one big mystery. Why does it work? So I'll separate it to two mysteries. So one of them, that we have generalization, meaning the difference between a trainer and tester, despite this over-parametrization. What do I mean? So we had a lot of discussion in the previous talk. I'll just mention this again. Suppose we have data points, and we want to fit them using a function, like a neural network. Then if we have tons of parameters, of course, we can fit exactly all the points. But if we usually want to use a simpler function, get better generalization, so you have a new point, you'll have a better performance. You don't want to use so many parameters, right? So, but as was mentioned earlier also, that even if we don't use explicit regularization, just use SGD on those ResNets, whatever, or the new types of networks, you can get really good performance in the tester, even with this tremendous over-parametrization of times 1,000 parameters than the number of samples, which is a great mystery, which I will not discuss here today. Today, I will focus on a smaller problem, but not much more modest than that. Is just, suppose we have just the empirical loss function, which is the W is the vector of all the parameters, and you have the loss function, and this is the sum of all the samples you get, the data points. And what you do usually, you optimize this using stochastic gradient descent, the SGD that was mentioned here. You just go choose a sample or a mini batch of sample, and then you decrease your weight, and you change your weight in the direction that decreases the loss. So a very small problem is, but still a long time with no answer, is why SGD converges even to a low training error. And that seems to be that it's the opposite case. The over-parametrization is bad for generalization usually, but here over-parametrization actually is helpful. It makes optimization, training error lower. Like it's easier to do this optimization. Now we'll talk about this more rigorously and try to mention why is it helpful. So again, to sharpen the point, so if I have some arbitrary loss functions, very complex in high dimension, you could have a local minima, which is bad, meaning it's high. Empirical loss is higher than the global minima, and if you start from a random initialization, you can get stuck in this bad local minima and not go to this global minima. But as we'll talk later, that's not what happens usually in many cases in the common neural networks. Okay, so before I go into that, so just some basic properties of SGD and neural networks. But we know that under some technical conditions, SGD converges to stationary points, meaning the zero gradients. It's a known result. Those points can't be strictly saddled. They can't have like non-unstable directions. And this is also true if you use gradient descent, like all the batch, not just samples. Also, we know that it's probably hard to do what I just said, to go to the global minima, because neural networks are highly non-convex. We know that multiple local minima exist. You can construct them. So naively, SGD should get stuck in those bad local minima. And there are many hardness results starting from long ago till now recently. We heard also some of them. So for example, you can have one neuron and have exponential number of bad local minima you can get stuck in. So you can construct problems which you have those difficulties. So the question is why usually it doesn't work. Yes?
Because it's stochastic, it's not quite zero gradient, right?
So it's the expectation. Like that's what's in the Boutou paper, expectation of all samples. Yes. So empirically, what we find is that actually the training does not depend much on initialization in many cases. Sometimes, if you can build, of course, examples it does, but in realistic data set it seems not too much. And also it's an interesting empirical result that if you let the training converge to the global minima and then you do some interpolation between the starting point and the end point, and you look on the weights on this path, then the loss function changes smoothly. So it seems to just go very smoothly to this global minima. And it's not, if there's so many it's non-convex, why is it happening? People once thought that because it's stochastic gradient descent, you just jump from those local minima until you get to this good local minima. But it doesn't seem to be the case, maybe. Again, you have similar training error on all local minima. It seems to be, again, if you do a lot of initialization, you find to be true empirically. And in this paper that investigated this and showed this result, they had some analogy in high dimension. Okay, so if you just take a Gaussian random field, it's just like a Gaussian process, just in many dimensions, zero mean and some stationary covariance, you get that all local minima are very close to the global minima in the error. So it's some interesting analogy, statistical mechanics, but it's not really clear what is the thing that makes it have this property, right? Why certain networks you can get stuck in bad local minima, but how can you separate those cases from the typical cases where it's not a problem? So it's high D intuition. So we have 1D. I can draw 2D of this carton, but I can't really have this also high D intuition. So let's give a very simple example wherein we can explain exactly why there's no problem in some cases. So suppose you have one hidden layer, D0 and D1. Sorry, D0 is the width of the input, D1 is the width of the hidden layer. If the number of those neurons is extremely large, much more than the number of training samples, then it's actually quite trivial to get zero training. Okay, so we start in a really trivial case. Why is that the case? Because if we just, for example, fit the last layer, we have n parameters, more than n parameters, n samples. It's easy. You solve a linear problem. You can get zero training error at the last layer. Okay, so that's kind of trivial, more variables in equation. But that's a big problem. You don't want to have this huge layer in the end. You don't have this case. It's in common neural networks. This is D0 times n, the number of parameters. It's much larger than in common realistic neural networks, because D0 is actually quite large in those ImageNet data sets. So this was pointed out by many authors. It's actually quite long list that this is a known fact. It's not really new. But as I said, it's kind of a trivial case, and we don't really work in this case. But for example, we know that you can. I proved that if I won't show the proof here, but it's similar to the previous proof done for threshold units. You can do it for ReLU and MSE. You can prove that a global minimum exists. You can fit a network with just the number of neurons. It's just twice the number of samples divided by D0. So it's about, it means that you need about the same number of parameters and samples. Kind of intuitively, if you want to remember everything, you need the number of parameters and samples, and you have a global minima which has a 0 training error. Okay, so if you're interested in the proof, I can talk about this later. Training. Everything is a training, as I mentioned in the beginning. It's just, I'm talking about the modest goal of just talking about the training error. And then in the end, I will discuss how it might be related to the tester. Okay, so, yes.
Number of samples, right?
N is the number of samples, yes.
So as long as D1 is bigger than that, or does it have to be?
Bigger than that, yeah. So it's, of course, if you have a lot, it's improving. So this.
Why not just the number of parameters and the number of equal number of samples?
It might be true. I proved it just for 2. Maybe.
It is regression problem.
No, it's
classification problem.
so it's regression. Yeah, I had any type. Sorry, I assumed 0.
You just have set of equality constraints, and you just have enough parameters, then you're done.
If you have enough parameters, you're done. But
I mean, same number of parameters as a constraint.
Okay, so it could be that you can decrease this by this factor of 2.
N over D naught is less than 1, you only need 1.
What? Sorry?
N over D naught is less than 1/2, you only need 1.
Sorry.
So N divided by D naught
Yes.
is less than 1.
Yes.
And you only need 1.
One layer, yeah.
Okay.
So D0 times D1 is the number of parameters, yeah. So if you have more, okay, so I'm just saying that you can do it with the number of parameters about equal to the number of samples, and the question is, can you get low training error with mild overparameterization of this and not this extreme overparameterization, and not only train the last layer? Okay, so I'm talking about training the internal nets. Okay, you have this global minima, it exists. Can you get there by training using SGD? Okay, I can go to the proof in the end if you want to say maybe why it's non-trivial. I think there's some complication there. Okay, so I just mentioned previous results. Oh, I had some. So we have previous results that prove the similar case with random. You just replace all the functions, the nonlinear functions, with random variables, like 0, 1 random variables, which is quite an extreme approximation. There was a recent work that showed the convergence in the tester, not training error. It's more stronger than this. If you have a consnet with non-overlapping parts, which I think something wrong in the animation here, it means that the number of parameters is less than D0, less than the dimensionality. So it's kind of very low parameters. You can't get a universal approximator. It's a restricted model. You can modify the training. If you initialize the training from some point which is close to the teacher in some way, or it's kind of cheating, then you can also prove convergence. You can have a tensor method, which is not the common way of SGD, which you can get convergence. You can have some strong assumptions on a target function, like linear separability. So if you're trying to learn a linear separable function, you can also get low error. And there's also a nice extension by Safran and Shamir that show that you have this clustering, which is kind of close to near linear separability. You can also get convergence. Also, there's other results that show that if you have very wide hidden layers, like D1 is polynomial and D0, in many cases it's much larger number of samples in a data point, you can also get convergence. Also, there's additional assumptions, like the target function is polynomial, or activation functions are polynomial, which in common cases is quite a strong assumption. Okay, so there are a lot of people have tried to approach this and stronger questions, and there's still something missing there. So I'll do some bit of notation and then just go to the results. So data point is X, N is the number of data points, D0 dimensionality, Y the target, W the weight of the first layer, Z the weight of the second layer. And we have some leaky ReLU, like more general than ReLU. You can have some slope here. which is rho, which is of course different than 1. If it's 1, nothing works because it's linear. Like nothing works in the proof. And the slopes I'll denote it by a. A is the function, which is the slope. It's either rho or 1, depending on the input. Okay, so the output of the network, if it's v, v is a vector of the output of the network on all n samples. And e is the error difference of this v, the output from the desired output y. And we just use a simple quadratic loss, which is 1 over n, and the mean square error. And I will focus here on differentiable local minima. Okay, so I'll even make it even a smaller problem. I look at points, like the local minima, in which we don't, if you look at the input of some ReLU, you don't touch the threshold, like the point where there's the non-differentiability. Okay, if I assume I only look at those points, then the next result will be relevant to that. Okay, we're not discussing non-differentiabilities or saddle points. Okay, so these are the notations. And before, I just need to define what I'm doing. So the mean square error is divided to different regions. Yes?
Can you elaborate on the assumption?
Which assumption? Non-differentiable. So
Why can we ignore points at which you're not?
So I don't think we can ignore. Well, numerically, what we found, before I answer that, so numerically we found we don't converge to those non-differentiable local minima. I have a graph in the slides in the end. We checked. We did a lot of initialization and decreased the learning rate to really low values, and the u never converged to 0. So it was always a finite distance from 0, and this was for a much. The MSC could converge to 0, but the u did not converge. So empirically, we couldn't find any evidence of converging to those differentiable local minima. But I'll think you might be able to extend the proof to those non-differentiable local minima. It should be probably harder. Okay, so that's my only claim here. I'm not saying it's impossible to converge to these. Okay, is that okay? So differentiable regions. Okay, so MSC has some non-differentiabilities, and we can divide it to different regions in which we are differentiable. Remember, A is the slopes of the input, the neurons. So W times X is the input to all the neurons of all over data points. So A, given the slopes, all the slopes of all the neurons and all the samples, you can define, this defines you uniquely the differentiable region. Okay, so the slopes give you exactly in which differentiable region you are. And this is a subset in the weight space. So just one more definition before I start giving results. So another matrix which is important to define is it's called the Qatari-Rao product. It's not really matter the name of it. So it's this concatenation of Kronecker products between the slopes and the inputs. You can think of it as some kind of amplified input matrix, which is take all possible inputs and kind of do a Kronecker product for every possible activation slope. Okay, so that's it's important to know that this matrix has the D0, D1 rows and n columns. D0, D1 is the number of parameters, and n is the number of samples. Okay, so now let's get started with some results. So we know, you can prove, soon I'll show how the idea. For all the LMs in one differentiable regions, all the differentiable local minima, the error is the same. Okay, that's easy. And also that this matrix, A Qatari product X times E, you remember, is the vector of the errors, the difference between the output and the desired target. This thing is equal to 0. Okay, so these are two important things we'll use later. So first, I'll just mention quickly how is it proved. So what do you need to do to prove it? Just take the output of the function and you can restructure it. Just define the weights. You can fold the weights of the second layer into the first layer. Define some other weights called W tilde. And then you can see that in one differential region you actually have a quadratic. It's a quadratic MS. The mean square error is actually quadratic. It's just some vector of parameters times this matrix. That's why it's important. Okay, so seems quite simple. There's some subtleties here. No, okay, so now if we are a differentiable local minima in this WZ and it's fully parameterized, it means that there exists no direction of descent. Therefore, you also differential local minima in the W tilde case. And therefore, at the DLM, you have this, the MSE, the gradient of the MSE is equal to 0, which means that this is what you get. Okay, this is just a first order condition on W tilde. So it's a very simple proof, nothing very deep, but you need to have this. Okay, so why is this important? So because we have this this is a matrix times E equals to 0. So what do we know? If the rank of this matrix is equal to n, okay, remember there's these number of parameter rows and n is the number of samples. If the rank is the number of samples, then just have a linear equality, means that E equals 0. So all global minima here, all differentiable local minima are also global minima with 0 error. Okay, so it's kind of very easy. So now all you need to do is trying to constrain the regions where the rank of this matrix is not this case, okay, or close or far from this. So intuitively, suppose A and X are some just random matrices. So it's not the case here. But if it's just some two random matrices, it's easy to show. It's a few lines of proof using determinants. I can tell it in a minute or so. That the rank of this matrix is exactly n. It's full rank. Okay, so it's kind of intuitive, like random matrices are full rank with high probability. It's not very surprising. Okay, but in our case, this is not every matrix. A is a discrete matrix. There's two values here, and moreover, it depends on the weights and X. Okay, here they're assumed to be like independent random matrices. So this is a problem, right? So for example, if if it was a linear network, this would not work. The rank of n, the rank of this matrix was d0, the rank of the input. Okay, so, but intuitively, if you have this nonlinearity and nothing is like really crazy, then W and X is doing something, then it should be that it seems like with high probability you would not have error. That's kind of the intuition behind the proof, but you just need to show this rigorously for W, like with this connection with W and X. And now the question is, can we quantify it? So how do we do this, like more rigorously? Again, remember we have those differentiable regions, and each differentiable region has an infinite volume, right? You can always increase by a scalar constant all your weights, and you go farther away. There's no limit. So there's no really volume to those regions. So what we define is the volume is just a solid angle. Okay, suppose just randomly sample a weight matrix. The probability to fall in one of these regions is given this probability, and we define by the volume, the angular volume. We have some expectation here over the data. It's not, you don't have to do it. Just for the simplicity of the next result, you can do some high probability results with high probability over the data. Okay, so just for simplicity, I'm taking the expectation over this volume. Okay, so this defines the volume of the different regions, and we want to quantify or to show that in the regions with we have the regions with bad local minima, like with high training error, are very small in comparison to the regions with good global minima. So they have global minima. So just a last bit of notation, those bad suboptimal regions, we define them by the local, like L epsilon. Epsilon is the error. So we use the classification error, not the square error. And there's the good regions, which contain the global minima, in which the classification error is 0. And now we want to quantify this angular volume of both regions. Okay, so to show that when is this the region with the bad local minima is much smaller, exponentially smaller than the region with the global minima. So okay, so now the results lie. So the main result is that those exactly vanish exponentially, and we take the asymptotic limit of n d0 d1 go to infinity in some form. And then we define this as the leading order inequality, meaning we just care about what's the leading term inside the exponent. Okay, when we define this inequality, so the first result, and we have some constant which depend on the error. So I first mentioned the other assumptions, but just before that I'll say there's 4 assumptions here. So the first result is that the area, the angular volume of those bad local minima is exponentially decreasing, okay, with this product of n and the dimension, and also depends on the error. So if the error is very small, it can become slower and slower. Also, we have a separate bound, which lower bounds the regions with the global minima. And given those two bounds, it's just easy to divide them and show that, using other assumptions later, then we can bound this ratio between them and get that the regions with the bad local minima are exponentially vanishing in comparison to the global minima. And OK, so now the other assumptions. So this is the strong assumptions. We have a standard Gaussian input, meaning no correlation, just a spherical Gaussian. So one, it's not a realistic assumption in any way. Just the correlation might be bothersome, but in many cases you do a pre-whitening of the input when you do a training of the network. And if you consider the network also to be in the last two layers of a very deep network which you randomly initialize the weights, it was shown that you have much less correlations in this case. It's kind of randomized.
Only second order?
Sorry?
Only second order correlations matter?
Only second order correlation. No, I just.
Whitening will not help.
No, I know.
Still not Gaussian.
No, I'm just saying the correlation, the no correlation assumption is strong, but it's also true that the higher order correlation matter. I'm just saying it's a weak assumption. I'm just saying that what people bother with the fact that you know they have strong correlation, but of course there's higher.
So non-Gaussianic.
Yes. Okay. So I think if it might be that the proof, if you have sufficiently strong large inputs, you can use some central limit theorem arguments maybe to make it weaker than just assuming Gaussian. Okay. So it might be that those correlation will become smaller, but this is only a speculation. So another assumption that the input is also large, so it's between n and the square root of n. Okay, if it was n, it's a trivial case. We don't need to worry about that, because if the dimension is larger than the number of samples, of course, even a linear network can do that. This case is actually quite reasonable. We calculated for a few networks. It's actually, I think for many data sets around the ratio between them is like 1 by 100. Like, so it's okay. Okay, and this is the nice, I think, progress, maybe than what was before, that the number of neurons you need, again, we don't want them to be larger than n. That's trivial. So in this case, we only need them d0 to d1. The number of parameters only need to be larger asymptotically than n times the log to the fourth of n. Okay, so it means that the number of parameters is kind of.
Daniel, what is
yes.
the thought about the inequality sign?
This is defined here. It means that we can have some lower order corrections which are unimportant. Okay, so this is kind of to make it easier on one slide. Okay, so the number of parameters is just around, with logarithmic corrections, around the order of n. You can still get this ratio of low training error. Okay, so that's kind of the main result. Any questions? This is a good time. If not, I'll continue. Okay, so yes, so just again to explain the result from previous. So before we had the trivial case was d1 equal to the number of data points. So this is kind of improvement over that. Okay, so just numerically, are we kind of in the right ballpark? So if you just take a random synthetic data set, Gaussian or MNIST, and you change the number of the d together, so the number of parameters divided by the number of samples increase. So if the number, you have some kind, I'm not sure if Phaeton is not the correct word, sorry, it's not. Somebody else put it there. I should delete it. But what you see is that if you go above the number of parameters, above the number of samples, it seems that you don't get high training error, which is kind of corresponding to what we assumed. And this is also seemed to be the case in larger data sets like CFAR and ImageNet, where you get really close to zero mean square error when the number of parameters is close to n. Okay, which I don't know, like previous results that showed similar results, they had 1,000 times more parameters, so it's kind of maybe an improvement in that case. And this was done by Elad, this simulation. Okay, so so far we talked about training error, which was completely non-interesting. I don't know if whether you care about training error, But what about test error? So this is not just maybe to future work. I'll just try to explain my idea. So we have this theorem that showed that the bad local minima, those have high training error, the lower bound by some bound. Okay, this is the angular volume of the regions in weight space, and this is the number of neurons. So we have this bound, and we had the lower bound on the global minima, the volume of the global minima in the training error. It's a lower bound. And we told you, I told you that if this bound is higher than this bound, then in this case, those global minima dominate. They have much more, so maybe you converge to them. And but that's only a training error. So another result, you can improve this bound if you add an additional assumption of a teacher, meaning you have a higher lower bound. Okay, and if you converge to this global minimum of the teacher, then you would have good test error because the teacher then generates the samples. Okay, so if you have this lower bound, and right in this region you have the underfitting. If you're in this region, you can converge to a local minima of high training error. So the goal is maybe future goal is trying to find a higher upper bound on those global minima which are due to overfitting, meaning that they get bad test error. Okay, so if we can bound those overfitting global minima, then in the regions we have, if you have a lot of global minima which have zero training or which are higher than the teacher, then we have bad test error. But if we're in the region inside both areas, you might have good test error. Okay, so this is kind of the idea, and that's the idea. Okay, so to summarize, what our motivation is why FGD often achieves low training error in multi-layer neural networks. Our result was that with standard Gaussian inputs, which is the strongest assumption, and mild over-parametrization. Also, I mentioned that Gaussian input was used by most of the previous work. Okay, so it's still a strong assumption, but it's not new. Okay, so mild over-parametrization, we mean the number of parameters is around the number of samples, which is kind of similar to what people are now doing. And we showed that the suboptimal DLMs in the training error exponentially vanish than global minima. So a lot of open questions, of course, is trying to extend this to deeper networks. And what can we say about saddle points, non-differentiable critical points? Because if we don't talk about these, we can't really, still not clear how if the egg carton shape is true. And another thing you need to do is, okay, so if you have this geometrical property, it still does not guarantee that you converge those global minima. So can you prove this convergence? And the last thing, of course, is generalization, trying to say something about test error. This is kind of tried to explain in the previous slide. Okay, thank you very much. Special thanks to Eric Ramon, Dan Carmon. Yes, they're both brothers. And Ziad Abbasi. And if I talked about training error mostly. If you're interested, there's some cool results that might relate to previous talks here about generalization. Train longer, generalize better, closing generation gap. Just a recent preprint on arXiv that show that if you have large mini batches, you can also get a good generalization error, and there's some nice diffusion model there that could be related to what was discussed here. Okay, thank you very much.
Questions?
Yeah.
So if I remember correctly, the regions in which the bad regions, size of those are exponentially small.
Hmm?
The regions in which the training error is zero is also exponentially small.
Hmm?
Most time you end up between 0 and epsilon.
What most time? Sorry.
Well, if your bad region is exponentially small, you're not going to get the region in which the training error is zero is also exponentially small.
I can't really hear the question. Sorry.
So the regions in which the training error was zero
Yes.
was exponentially small, right?
Yes.
But you convert.
It was a lower bound. It was a lower bound. The lower bound is a region which is extremely small. Yes.
It has to be sort of finite volume to get that, right?
how do you get dash lower bound? Sorry. Okay. Sorry.
Question? Okay.